thank you for inviting me for this panel discussion. It's a very important topic, and my topic would be ultrafine materials for sustainability of concrete construction. So before I start, I would like to also showcase some of the products that we are launching. So most of the products, if you see, they are common, but here we are talking about certain new kind of concretes. So we have developed a R.E.C. shieldocrete. So this is a new, non-conventional concrete. If you see, in just one hammer, you can break it. But this was done live in Goregaon, and a challenge was given to all the participants. Whoever could break it in one shot, would be given a prize money of 1 lakh rupees, and no one could do it. So the same cube, was presented in front of all of them, and no one was able to break it. Now, after this is conventional concrete, and if you see in conventional concrete, if you expose it to a very high temperature, say 1000 degrees Celsius, the aggregates start blasting. They just shoot out like bullets. If you're able to see the video properly, so you'll see some bullets like aggregates flying out. And this CSH gel, it loses water very fast. So it turns into steam. And whatever aggregate is there, which is stuck, it shoots like bullet. And within few seconds, this video was just 30 seconds. Within 30 seconds, the concrete is gone. This is RTC firecrete. Now here, we keep on hitting it for a long, long time. And despite that, it does not undergo, the aggregates do not pop out or they do not come up. The heat is, absorbed inside the concrete. And the concrete gets converted into another, the previous conventional concrete, if you heat it and you try to hold it in hand, you won't be able to hold it in the hand even on the other side because the heat transmits very fast. Whereas in this concrete, the heat is trapped, in the top surface, and anyone can hold this concrete. After this heating is over, immediately anyone can hold it from the bottom and lift the concrete. So heat does not transmit. And if you see, this concrete is getting converted into a glassy kind of a material. So this is also one of our, new, contribution to our construction world. This is, being applied in few projects. We are trying to also go for patent on this. Now, this is our last development. So if you see conventional concrete, sulfuric acid is the most dangerous one. No concrete can last in that. This acid-resistant concrete, the guy has not been able to keep it out for a long time because it's very concentrated. It can get affected. We have developed this acid-resistant concrete which can withstand even serious acidic states. And there are certain textile industries where they are using, because for treating the textiles, they use sulfuric acid. And earlier they used to change the flooring every 6 months, but now it's been almost more than 6 months. It's 1 year, and the flooring is working perfectly well. So these are some of the new things that are happening, and what is possible in concrete, in future. I was trying to showcase that. Now with this, I would like to start on these ultrafine materials for sustainability. Some of the products that I showed you do contain ultrafine materials, not all of them. And certain materials come nano-engineered material. So, basis that we are able to develop many new kinds of concrete. Now, if you see, what is the brief history of concrete? So, our Bharat, I think, is the leader in construction, because we used lime mortar for masonry. And this lime mortar, we had two technologies. One was lime mortar and mixing urad dal or this, urad dal, I don't know what you call in English, the cereal, the black cereal, along with jaggery. So the technology was, if you see the Greeks who used lime mortars, their technology was that lime was burnt, carbon dioxide was released outside, and this lime was mixed with sand and water, and then slowly whatever carbon dioxide that was left outside, reacted back and formed calcium carbonate again into the structure. So there was no problem of carbon dioxide release, carbon dioxide issue. Okay, that was a good technology, but it was very, very slow. But Indians, we had a fantastic way of accelerating this. And we used urad dal and jaggery. So whole night it used to ferment, and this fermented yeast used to produce carbon dioxide. And this was mixed with lime. And when carbon dioxide was released inside, this reaction happened much faster, and we got a stronger concrete or stronger mortar much faster than the other world. We also used surki. So surki was where we used burnt clay or burnt brick powder. And this burnt brick powder along with lime, they give you something similar to CSH gel. And this was already there in India. So whatever happened later, like Romans used pozzolana cement, that's pozzolana, pozzol from a volcanic ash. They used that with lime. In 1824, Joseph Aspdin did something that Indians were doing for a long time, and that was lime with surki. So he actually mixed lime with burnt clay, and that is how the idea for starting cement was there. And uh, sorry, not Joseph Aspdin, it was the guy who built the lighthouse, John Smeaton. And after John Smeaton came Joseph Aspdin, who basically mixed limestone and clay and then burnt it together. That is how the birth of new modern cement was done. After that, in 1849, Joseph Monier did, and then first concrete road was built. In 1930, uh, uh, many new things started happening. Air entraining concrete was done. Fly ash was being used for manufacturing concrete. Ready-mix concrete was introduced for the first time. Hoover Dam was getting constructed. And then after that, slowly, or the development started happening much faster. And today, if you see the rate of development or rate of change that we're seeing is much faster across the entire century or half the millennium. So the reason I've tried to show this to you is the concrete is evolving continuously, and there is something that is happening in the evolution process. Now, what happened parallelly when this cement was getting developed? Cement was getting also replaced by fly ash and silica fume and GGBFS, thereby reducing the demand for energy. The cost also reduced for manufacturing concrete, and it also showed fantastic performance, like fantastic durability, reduced alkali silica reaction, better utilization of resources. And if you see, globally, it got adopted across the world. Today, fly ash and GGBFS are being consumed the most among all the available supplementary cementitious materials. From OPC, we have now moved to binary blends. And the reason are all these. Now, what basically is the problem? The problem with pozzolanic materials is it's very slow. These supplementary cementitious materials. You are able to get better durability, lower what do you say, carbon footprint, all those benefits are there, but at the cost of strength development. Today, we require more concrete, faster concrete construction, and that is not possible, with the slow pozzolanic materials that we are using. Some people have developed the main challenge with us in India or across the world is most of the engineers are following thumb rule. So if you ask them to change the mix design for 3-day early strength or 7-day early strength, they are not able to understand what is the difference between using a pure OPC mix and OPC plus flash, and everyone goes with OPC plus flash or slag. So and also the codes, the standards also follow the same practice. Nothing changes much faster. So everyone is if he's using flash, he'll keep on using flash, no matter what what age strength he requires. Or so if you see, this is the problem today with the supplementary cementitious materials. the time that is required to complete the project is higher because the cycle time and the time required for curing or developing the strength is much higher, and it is resulting in such kind of problems. Now, how do we reduce the cost, or how do we accelerate it? This is where ultrafine materials come into play. Ultrafine supplementary cementitious materials. So if you see from history, cement, its efficiency improved when we increased its fineness. And taking same cue from cement, if we start manufacturing or try to process these ultrafine cement, supplementary cementitious materials into ultrafine range, much finer than cement, we have seen a lot of benefit. And this includes fly ash and slag, which is almost 10 times finer than cement in terms of surface area or diameter. And it gives much better strength even at early age. Almost 70 to 80%, of 20 day strength is achieved in 3 days or 7 days. It does a very good particle packing, so it fills all the capillary pores. The pores are responsible for getting lower strength, so it fills those pores. It is much highly reactive. Um, uh, so if you see the picture on the right hand side, the cylindrical thing that you see is a human hair. Okay, that's a microscopic view. So what happens is, in one human hair, there could be the diameter of that could be equal to 10 particles of ultrafine cementitious materials. And one particle of ultrafine is 4 particles of microfine silica or microsilica. So that is the comparison. So this is what is possible today, and this does much better work in terms of filling the voids. It increases the reactivity. It improves the durability. So you get much better performance in ultrafine in terms of, and the best thing to do is it start incorporating in mixed design. The IS codes have been released. There are some of the real world case scenarios where, so even in India, many projects have started using this, and a lot of success stories are there. So it is only the material innovations that will help us in going green, and also, give the answer for the challenges that we face. So that is it from my side. Thank you.